Hello to all my dear friends. I am your friend Aishwarya Sharma, Civil Wallah, welcoming you all on the platform Gate Wallah English channel. So guys, today we are going to see our last lecture on RCC. Actually not last sequence wise, after that we will be watching one more lecture, and that would be basics of working stress method. But yes, as per the syllabus of GATE, this is the last lecture. So today the agenda is pre-stressed concrete. So we are going to see all the important aspect of pre-stress concrete in one shot, and all these are the topics which we have to cover today. So first of all, we are watching what is pre-stress concrete. After that, why do we need high strength of grade of steel and concrete in pre-stress concrete? What all are the various types of pre-stressing, advantages of pre-stressing concrete over normal RCC structure, and the analysis of pre-stress concrete, the most important one. Okay, so dear, first of all, why pre-stressed concrete? Okay, what was wrong with normal RCC? Actually nothing was wrong with normal RCC structure, but what happened there, designs are also there, we know the entire code is there, we have studied that in our 1 to 2 semesters in our colleges, your normal cracked sections RCC, but pre-stressed concrete is basically your uncracked section. It is a concrete which is already stressed. What is the necessity of that stress? So we intentionally are going to produce stresses of such nature and magnitude that it is going to counteract our external stresses, or you can say the stresses due to external loading. Okay, so all these are the advantages of our pre-stressed concrete. Okay, or you can say that in conventional RCC structures, not full section is utilized properly, because we know that concrete is good in taking compression, but in tension zone it is not able to resist crack. Okay, so tensile cracks were there, and we actually ignored the entire cracked portion in our conventional RCC. So if you are giving a provide of 300 by 600 or 400 or 500 like that, so out of that cross section, only compression zone part was effective, and rest of the part was used only to hold the steel, or you can say to hold the tension reinforcement, or to hold the shear stirrups or torsional reinforcement, like that. So effectiveness of the concrete was not there. Okay, concrete was not effective throughout the section. Okay, but now when the introduction of pre-stressed is there, now we are already going to apply a compressive stress on our concrete structure. Now what will happen as a consequence? Whenever you are going to apply external load, due to that most of the stresses would be counteracted. So still there would be no resultant tension. If there would be a resultant tension, then it would be of such magnitude, then it is not going to exceed your permissible stresses in tension. Okay, so basically a pre-stressed concrete in which internal stresses of suitable magnitude and distributions are introduced, such that the stresses resulting from external load are counteracted to a desired degree. What is the desired degree? Either no tension, or if tension is coming on any part of my beam, it means in that case you can say it would be under the permissible limit, isn't it? Okay, now what are the benefits? So see, whenever we are doing the pre-stressing, now what is happening? The entire concrete section is in compression, and in conventional RCC what happened? Section was effective only till neutral axis, and actually you are paying more for concrete, and relatively you are paying less here for concrete, isn't it? So that is the reason why we are going for pre-stressed structure. So nowadays you might have seen that most of the metro bridges in metro cities, they are pre-stressed concrete slabs. You can see that the high amount of dynamic load it is going to take within a very thin section. The reason is that entire section is effective for taking your stresses, isn't it? And so what is happening in pre-stressing? So to utilize this section more effectively, because if this cross section is already in compression, so now it is going to be utilized more effectively. So we are going to introduce compressive stresses before the application of external load. Okay, and those external loads normally could have produced tension. You can see that if this beam is without pre-stressing, then this portion is under compression and this portion is under tension. Okay, so that was the problem. If I am going to draw the stress diagram here, the diagram was like this, if I am talking about the linear distribution. So this is the tension zone. So you can see these concrete is going to experience the maximum tensile stress. So if I am going to compress this beam already, then it would be having some pre-captured pre-stress then, and now this portion will be less than this or equal to this, or you can say this extreme stress now will be less than this. So this is the extreme tensile stress. So our task is to keep this value less than this or equal to this, and even if it is slightly more than that, still there is not a problem. Okay, so that is the concept of pre-stressed concrete. Okay, to do this we need high grade of concrete and high grade of steel. Normally, you know, in your conventional RCC structure, you can proceed with M20 grade of concrete for normal construction and M15 or M10 grade of concrete for PCC, or grade of plain concrete cement for normal mass construction. And if it is a severe construction like construction near the seashore or underwater, then we need to go at least with M30. But my dear friend, in extreme conditions there you were using M30, M35 or M40, but pre-stressed concrete starts itself with M30. And same thing happens with steel. Normally in conventional RCC we used mild steel 250, HOESD bars 415 or 500, but in pre-stressed concrete we are going to use the steel wires whose value is how much? Whose value is greater than 1000, 1200 or 1500 Newton per mm square. What is the reason behind that? So first of all, let's discuss why do we need high strength steel? Why do we need high strength steel in pre-stressed concrete? Normally this pre-stressed concrete section goes through various losses, and if we are calculating the amount of strain loss, that itself is very high only due to creep and shrinkage, and apart from creep and shrinkage there are more reasons, but only due to creep and shrinkage it has been observed practically that there is a strain loss of 0.08% or 0.0008. If such is a strain loss, and for steel we know that Young's modulus of steel is 200 GPa. Okay, so if we are going to calculate the loss in stress, then the equivalent stress loss is 160 Newton per mm square. And my dear friends, these are the losses only due to what? Only due to creep and shrinkage. There are other factors as well, like creep of steel, shrinkage of steel bars, okay, frictional losses, okay. So many factors are there, elastic shortening of concrete. So if we are going to inculcate all such reasons, then this range comes around 200 to 300 MPa. And if we are going to use Fe 415 even, then the permissible stress for that in WSM is 230 MPa. So you can see that majority of the part is going to lost in the losses only. Sorry, excuse me. Yes, so majority of the part is going to lost in losses only. Okay, so we need to have high strength steel wires, maybe of the range of 1000, 1500, 2000, such that we can say that the losses are only 10 to 20% of the available strength, then your design would be good. Okay, this is the reason for steel. Now what happened to concrete? Why do we need high grade strength in concrete? So let's see that. There are two types of pre-stressing. That is my next topic. One is pre-tension pre-stress concrete and another is post-tension pre-stress concrete. Okay, so before this I would like to explain those two things, then I will come back to this slide. Okay, so there are two types of pre-stressing. One is pre-tension pre-stress concrete and another is post-tension pre-stress concrete. Pre-tension means tensioning process is done before. Post-tensioning means tensioning process is done after. What is that reference? This reference is casting of concrete. It means that if you are going to cast your concrete, okay, after the stretching of wire, or you can say if the tensioning process has been done before the casting of concrete, such sections are known as pre-tension pre-stress concrete section. And similarly, if tensioning process is done after the casting of concrete, then such sections are known as post-tension pre-stress concrete. Okay, so pre-tension, this method is very simple. It is known as Hoyer's method, Hoyer's Hoyer's method, Hoyer. So what we are doing? First of all, we are going to stretch a wire. Then we are going to tie those wire at the ends. Okay, we are going to anchor them in the abutments. After stretching, now it's time to pour concrete. And when the initial setting of concrete has been done, after that we are going to cut these wires. So whenever we are going to cut our wires, so due to the strain energy stored in them, they will try to contract. And due to the bond action between steel and concrete, your concrete is also going to contract. But the question is, the bond strength of the concrete must be very, very high. Then only this uniform contraction with compatibility can occur. Okay, so that is the reason, dear, why do we need high strength concrete in pre-tension pre-stress concrete. So what is the process? So pre-stress is just transmitted to concrete entirely by bond action between the steel and surrounding concrete. So what is the procedure which is there? First of all, steel tendons are placed in predetermined position. One end is secured to an abutment while the other end is pulled and fixed to the other. The concrete is then poured and hardened. Now the end of the reinforcement are cutted at the end, and between the members reinforcement tending to resume the original length. Okay, because due to the energy stored, now they will try to come back to its original position. So due to this, compression of steel is occurring, and hence the compression of concrete will also be occurring. Okay, so since the bond action is the main hero here, so the minimum grade of concrete which is required to meet this bond action is M40, okay, because we know if the grade of concrete is increasing, then its characteristic compressive strength, if it is increasing, then shear strength, bond strength, ductility, okay, tensile strength, Young's modulus, all these other properties are also increasing. Now what happened in post-tension pre-stressed concrete? In post-tension pre-stressed concrete, first of all, you are going to keep a duct and you will cast your concrete. So while casting of concrete, you can keep the duct inside that in desired shape. And after casting of concrete, what you are going to do? You are going to insert steel wires through those ducts, and then you are going to pull it. You can do the pulling either from one end or from the both the ends. Okay, so by pulling the wire and giving reaction to the concrete, we are compressing it. Okay, and eventually we are going to anchor our ends with the help of anchors. Okay, so during the pulling of wire, As a reaction, you are pushing your concrete, so your concrete is being compressed, it is being stressed. Okay, so the task was to give compressive stresses to the concrete. So we can do it either way, either pre-tension or it may be post-tension. So what is the difference here? Why it is called post-tension? Because in this procedure, tensioning process occurred after the casting of concrete, whereas in pre-tension pre-stress concrete, tensioning process occurred before the pouring of concrete. Okay, so what procedure is given here? A duct is placed inside the formwork where the tendon has to be placed. Okay, concrete is poured in the formwork and allowed to harden after curing. After that, tendons are placed in the ducts and anchored on one side. Here tendons are stressed by pulling with the help of jacks. It is known as jacking, either from single end or from double end. Okay, void between tendon and duct is filled with the grout, because whenever you are going to insert your wire here, so this void is also there, so we usually fill this void with the help of grouts. Okay, so now after that, after anchoring, tendons are cutted. Okay, so now let me come back to this slide. Why do we need high strength concrete? Now we know what is pre-tension concrete and what is post-tension pre-stress concrete. So to bear the high stresses at the ends, what happened in post-tension pre-stress concrete? A very high intensity of stresses are developed here, but these high intensity of stresses can be tackled with M30 only. So that is the reason why the minimum grade of concrete used in post-tension is less, because bearing is relatively easier with respect to the bond. So in pre-tension pre-stress concrete, entire stressing is based on the bond action, and in post-tension pre-stress concrete, entire stressing is based on bearing, or you can say and bearing reactions and bearing stresses. So and bearing is relatively easy than transferring force through the bond. Okay, so therefore here M30 will also work for you, whereas in pre-tension pre-stress concrete it is going to be M40. Okay, so to bear high bearing stresses, we will be needing high strength concrete. Okay, so where do we need to bear high bearing stresses? Especially in post tension, Okay, to bear high bond stresses between steel and concrete, where it will happen? Especially in pre-tension, Okay, and as you know that losses are also a biggest challenge in pre-stress concrete, as we have seen that losses due to creep and shrinkage are also known as the major losses. So if we will be using the higher grade of concrete, then the creep and shrinkage values would be less, because as we are increasing the grade of concrete, compressive strength of concrete, then the impact of creep and shrinkage would be less, because the quality of material will be more, so deterioration of the concrete will be less. So, and one more point, it also increasing the shearing strength of the section. Okay, so whenever stressing is done, so automatically it helps in improving shear. How? Suppose I have two blocks and they are not confined, then the relative displacement is easier. But if these two blocks are confined, now it is hard for me to get relatively displacement. Okay, so to increase the shearing strength of the section, we again need high strength concrete. Okay dear, so these all are the reasons why do we need high strength steel and high strength concrete. Okay, and these are two types of pre-stressing, pre-tension as well as post-tension. Okay, so key point is, what is the mechanism of pre-tension and post-tension, and the minimum grade used here is M40 in pre-tensioning, and in post-tensioning it is M30. Don't forget this. 2 to 3 times it has been asked in exams, GATE. Okay, now what all are the advantages of using pre-stress concrete? As I told you that first is, now you will be able to use the entire cross section, because entire cross section is having either compression or slight tension which is under the permissible limit. So first thing is, the cross section is utilized more effectively in pre-stress concrete, which results smaller section, and what would happen due to the smaller section? Dead load of the structure reduces. As a result, the supporting structure cost like formation of column, footing, slab, beams, okay, they will also reduce, okay, and they are also useful for a long span of a structure, as I given you example in the beginning that most of the metro girders. Okay, yes, one point I have skipped. If somebody asks you what is the examples of pre-tension pre-stress concrete, then they are railway slipper, electric poles. Whenever you want to achieve a repetitive type of work, repetitive type of section, so at that point of time pre-tension pre-stress concrete is very useful. And the best example of post-tension pre-stress concrete is slab which you are using in metro girders, okay, in metro bridges. Okay, so these are the two examples here. Yes, so I was telling you the weight of the supporting structure will also be less, like column, footing, slab, beam, they will also be reduced. I am not saying that the original cost of pre-stress concrete will also be less than the RCC. It's not like if we are using lesser amount of concrete, so you need to pay less. Obviously, for concrete portion you are going to pay less, but pre-stress concrete requires a more skilled labor as compared to our conventional RCC construction. You can see that conventional RCC structures can be done with the help of experienced laborers and all, but for pre-stressed concrete you need literally a diploma holder type you can say people who can conduct that work, or they need special training for that, okay, because equipments, stressing, all these things are a sensitive thing, okay. So it is also useful for a longer span of a structure, and yes, I explained you already, it improves the shearing resistance of the structure, okay. Now next is analysis. So before analysis there are some assumptions in the analysis of pre-stress concrete. The first is plain section before bending will remain plain after bending, okay. Second is within the limit of deformations Hooke's law is valid, means up to proportional limit stress is proportional to strain. And third assumption says that the stresses in the reinforcement are not going to change along the length of the reinforcement, okay, they are not going to change along the length of the reinforcement. And next is variation in the stresses in steel reinforcement due to external loading is ignored, okay. See, first and second are clear, plain section before bending will remain plain after bending, like in case of LSM, WSM, okay, plastic, anything. And since here stresses diagram are also linear, so they are depending upon strain, so stress and strain both diagrams are linear, means Hooke's law is going to valid. So third assumption is saying the stresses in the reinforcement does not change along the length of the reinforcement. If this is my structure and if I am going to pull it or I am going to compress my concrete, so there is a tension in the steel. So if you have applied here 1000 MPa, so this is 1000 here, but as you are coming inward, so due to the losses and all, it would not be 1000 here or here, it would be least here if jacking is done from both the end. But for the analysis point of view, we will be assuming it same. Next thing is, whenever you are going to apply some external load, then what would happen due to that external load? So when external load is there, deformation is like this. If deformation is like this, then there would also be extension in the steel wire. So due to the extension in steel wire, strain increment is there. Due to the increment of strain, stress increment would be there. So when these pre-stressed concrete members are loaded with the external load, so it's quite obvious that the length of the steel wires would be changed. Due to that, change in strain would be there, correspondingly there would be change in the stresses as well, but we are going to ignore that due to the external load. So variation of stresses in steel reinforcement due to external load we are going to ignore. Although we can calculate how much strain is there, we can calculate that with the help of slope deflection formulas of strength of material. we can find how much losses are there, or whether there is a loss of stress, or there may also be gain in stress, or there may also be loss of stress. So we can find that. Okay, suppose it is located at some constant eccentricity, then due to this it is going to expand. So due to this, so if E is the eccentricity here, so one time increment is E theta, here increment is E theta, so total increment or total increase in length is 2 E theta, and increase in strain is 2 E theta upon original length into 100, and stress you can multiply it with Young's modulus. Okay, so total 3 methods are there for the analysis. The first is stress concept, quite basic, you might be knowing this. Second is slightly, only one new thing you will be able to know here, load balancing concept, and third is P line C line method. So what is happening in the stress method? We are going to calculate the effect of each and every force. For example, if this is my pre-stress concrete and it is loaded at some eccentricity E, so this is the cross section here, this is the cross section. So this cross section is going to experience with a constant force P by A, which is acting uniformly throughout, and due to this eccentricity, the lower portion is going to compress more and upper portion will try to come in tension. So overall tension or compression will come, that will depend upon the resultant of these two. So this is PE upon I into Y. Okay, PE upon I into Y, this is P over area, and due to this, this is due to the external load. So due to external load, you can see that sagging would be happening here and hogging would be happening there. It would be M upon I into Y. So the resultant stresses would be at top fiber is P by A minus PE upon I into Y plus M upon I into Y. Why I am saying minus here? Because if eccentricity is done below the centroidal axis, then upper portion would be in stretching due to pre-stressing only. Okay, and what would happen to stress in at bottom? P by is there, it is plus PE upon I into Y, and it is minus M upon I into Y. So you can see these both are going to cancel each other. So this eccentricity has been decided based on the external load stress condition, so that there could be a resultant compression throughout. Okay, and final stresses may be like this, it may be like this, or it may be even like this, small tension. But one thing is sure, the sum of stresses at top and bottom fiber is going to remain constant. Whatever is there, same magnitude is there as well. Whatever is there, same magnitude is there as well. So this plus this plus this plus this plus this plus this and this will be cancelled, this and this will be cancelled. So we can say the sum of stresses at top and bottom fiber is going to remain constant, and that is equal to 2P by A. Sum of stresses at top and bottom is going to remain constant, and that is equal to 2P by A, isn't it? So this is stress. So we can say here that due to pre-stressing, two components are here, and due to external load, one component is here. Okay, so P upon area is the component due to pre-stressing force, and PE upon I into Y is the component due to the eccentricity of pre-stressing force, and that is M upon I into Y, isn't it? Okay. So final stresses I have told you, final stresses are P by area minus plus or plus minus PE upon I into Y plus minus M upon I into Y. So no need to take tension if eccentricity is varying. So whenever you are going to target a particular section, for example, now you are targeting this section. Suppose if eccentricity is varying, it is triangular or it is parabolic, then all you need to know the exact eccentricity of that corresponding section. Okay, so like here in load balancing concept, we have seen that it would be like this. It is not very correct, it is like this. Forgot to edit this. Okay, so here if I am going to apply force, it would be like this. Okay. So such varying eccentricity can also be solved by stress method. But what we are going to do for such scenarios, what we are going to do, we will be stretching this wire and make it zero eccentricity. And due to this stretching, there would be an upward point thrust. So we need to know that point thrust. We know that this wire is pulling out here with a force, let's suppose P, here also with a force P. If this angle is theta, then the upward component is P sin theta from this side and P sin theta from that side. So it is going to be 2P sin theta. So if you want to stretch this wire and you want to make it straight, then a upward point load of 2P sin theta will be coming here, just like this, okay. So this is P in this direction, okay, this is P in this direction, although I am correcting it, but this is a very minor angle. So cos P into cos of small theta, P into cos of small theta is almost, it remains P only. So it is not going to make a huge difference here, okay, it is not going to make a huge difference here. So here you can see that it is originally like this, and now you have made it like this, okay. So this is the equivalency of the load balancing concept. So instead of this varying profile, you just had given 2P sin theta upward. So now these stresses can be computed due to this constant eccentricity. Now the stresses has been computed due to this constant eccentricity, which is 0. So what is going to be the stress here now? What is going to be the stress? Stress here going to be P over area plus minus P into 0 upon I into Y, because eccentricity is 0 now, okay, minus plus minus M upon I into Y. All you need to keep one thing in your mind: earlier for M, external load was responsible, but now while you are calculating the value of M, the combined effect of W and 2P sin theta are going to come into picture, okay, they both will come here together, okay. So this is the key point which you have to make. Earlier the M was only due to external load or dead load, this time M is due to the converted load as well as due to the external load. External load may be dead load, live load, combination of both, whatever, okay. Another thing can be, once again I am reminding you that it can also be solved with the stress concept. All you need to know the exact eccentricity, okay. This 2P sin theta you can also achieve like this. For example, what is the bending moment here? Let's suppose this is a eccentricity E. What is the bending moment here? Bending moment here would be P into E. If same bending moment is to replace with the upward point load, then let's suppose this is my upward point load, let's suppose W dash, and W dash into L by 4, WL by 4. So what is the value of W dash? It is 4PE over L, and this and 2P sin theta are same, because you can write here it is 2P upon E over L by 2. What is E over L by 2? It is sin theta, or you can say tan theta. So just to match there, I am writing it sin theta. I am writing here sin theta, okay. This is sin theta. So 2P sin theta. So either you can balance the bending moment due to load, or you can from mechanics you can draw the vertical component, okay. Next is bars with parabolic tendon. If there are bars with parabolic tendon, then what is going to happen? If there are bars due to parabolic tendon, then what is going to happen here? So first of all, it's my duty to convert this parabolic tendon into a straight wire. If I am going to do this, then what to do? If I am going to do this, then what to do? This is my straight wire, and here when, see, try to depict the bending moment diagram. So here the shape was, linear. This linear bending this shape of bending moment you will be getting from a point load. So an equivalency would you have developed in terms of point load. Here the shape is parabolic. So such shape is the bending moment of UDL. So here you are going to get a value of UDL in the upward direction. So similarly, if you want to, let's suppose this is your E and you want to get the value of this point load, let me call it W dash. So this W dash L square by 8 is nothing but P into E. So W dash is equal to 8 PE upon L square. So this is the value of UDL which is acting in the upward direction. So once you have removed this, you are going to place this, and after placing this, the resultant stress would be due to P over area plus 0 eccentricity, P into 0 upon I into Y plus minus M upon I into Y. Again you have to keep one thing in mind, that earlier this M had been due to W, now this M would be due to this W minus W dash. So this time M is the function of W and W dash both. Okay, it may be sagging or it may be hogging even sometimes, so don't discourage there. Are you getting it or not? So this is the concept. So if there is a case of linear profile, then apply a equivalent load. Okay, if it is a case of parabolic profile, then apply UDL. If it is a case of constant eccentricity, then load balancing is not going to help you. It will give you correct answer, but no, it is going to have a constant eccentricity. So you need to introduce that eccentricity. Basically, load balancing concept is the task of load balancing concept is to make your eccentricity constant. It may be 0 if it is being stretched at center, or it may be some other value constant if ends are at some other level. Okay, so this is the beauty of load balancing concept. Now the last is P-line C-line method, and in this method what they are doing, they are trying to find the locus of compressive thrust. So like we do have a cross section here, okay, like do have a cross section here, and it is subjected to some bending moment M. This M is the bending moment due to external load, So with respect to pre-stressing line, you will be able to calculate what is the eccentricity of compressive thrust with respect to your pre-stressing line. For example, your pre-stressing line is somewhere here. Let's suppose this is your pre-stressing line and this is your centroidal axis, and let's suppose X bar is coming out somewhere here. This is X bar. So this is the location of compressive thrust. So this time the calculations are to be made with respect to compressive thrust. So you are not going to use this earlier eccentricity. Earlier you were calculating it with respect to this eccentricity, but this time you are going to use the eccentricity of the compressive thrust, which is none other than this E dash. So E dash is X minus E, or if this green point is somewhere here, in that case E dash is E minus X. So depending upon its location you can fix it. So now if this is the point of application of the thrust, so resultant stress would be C over area. Numerically C and P are same, where P is pre-stressing force, or it is plus minus C into E dash upon I into Y. Okay, so this is the next concept. This is the P line C line concept. Okay, P line is your cable line. It is the line of pre-stressing cable, and C line is pressure line, thrust line. Okay, so first of all you are going to calculate the deviation of compressive thrust from your cable, and you have to calculate the revised eccentricity. Based on that revised eccentricity, you are going to calculate the resultant stress. Are you getting it or not? So this is the concept of analysis. Okay, so we have covered these three analysis procedure. Okay, and for numerical stay tuned either for Abhyas session or for my next series. Okay, but yes, one more lecture, it's going to come on Friday, day after tomorrow, and on that day I'm going to take the basics of working stress method. So that is also important for you guys. So thank you very much.